Next, we discuss number codes. And number codes is a modification of the usual binary number representation that we have already run, which is regarded as a suitable format for most digital systems. However, we notice that the more familiar digital system is preferred method of entry. In terms of input, again, or displaying data, you cannot read ones and zeros when you are presented to them from a computer screen. We normally require to be displayed data in a format that we are used to, mostly in the decimal format. Therefore, we notice that we need an interface that will allow us to, when we place our keyboard to enter number 3, that number 3 is received by a computer as a binary number. That is what happens in most digital systems. We do not work with binary zeros and ones literally. We normally convert. The computer uses binary numbers, we use the decimal numbers, and therefore there is always an interface that converts the decimal to binary and vice versa for the computers to display to us and for us to input our required data in the format that we best understand, which is binary numbers. So we say that codes are used as an interface or to enable the interface to do the conversions. And we say that codes that relate the decimal numbers to binary numbers have been formulated. And one of the most one is called binary coded decimal, which is normally known as BCD code. So we'll be looking at the BCD codes, but there are other requirements that would necessitate other forms of number codes beyond the BCD, and one of them involves measurements of angular displacement, in which case we might notice the binary format being error prone, and in such instances we use a different number code known as gray code. Well, another application that has been there in the past involves a number code called XS3 code, which was used in binary arithmetic operations. We are not going to be talking about XS3 in this course. We will concentrate on the first two, that is the BCD number or the BCD codes and the gray codes. So we start now on binary coded decimal or BCD. And for this to work, we simply represent each decimal number into its 4-bit binary equivalent, and that forms our BCD code. So for instance, you have a 9. 9 is represented by 1001, and that's it. We don't go beyond that. So we do not represent 10 or 11 or 12. We just represent decimal numbers 0 to 9 using their 4-bit binary representation. If the decimal number has n digits, then BCD representation will be 4 bits long. For instance, if we have a decimal number that has n digits, let's n be 3. So we have a number like 123. So we will not now try to convert this one into its binary equivalent. Rather, we will represent each of these digits using 4-bit binary representation, such that we'll have 3 is represented by 0, 0, 1, 1, 2 is represented by 0, 0, 1, 0, and 1 is represented by 0, 0, 0, 1. So this would form the BCD code that represents the 1, 2, 3. Therefore, the decimal digits 0, 1 to 9 are encoded by their binary sequences, starting with 0 as 0, 0, 0, and as you have already mentioned, 9 is represented by 1, 0, 0, 1. The rest of the binary sequences, that is above 9, that is 10, 11, all the way up to 15, are not used, and therefore these are invalid BCD codes, or they are invalid in the BCD format. So this form of BCD is known as 8421 code because each digit is represented or translated by the 4-bit representation with position weights that are equivalent to 8421. We said 2 to the power 0, 2 to the power 1, 2 to the power 3. So this is 8421. So this kind of a number system is called 8421 code. So other variations of BCD such as 2421 code have also been proposed, but they are not popular than 8421, and therefore we remain with the 8421 code system. And we want to do an example that says give the BCD code for this number. Very simple. We just take each digit, represent it using its binary equivalent using 4-bit code binary representation, and that forms our BCD code. So 151 is represented by 0001, 5 is represented by 0101, 0.2 is represented by 0010, and that forms our BCD code that is equivalent to 15.2 in decimal. Another example, we want to convert this one to its BCD code. You simply have 9 as 1001, 2 as 0010, and 3 as 0011. This is our BCD code for 923. So on the other hand, we might need to do conversion from BCD code to the decimal notation. And here we have an example that is asking us to obtain the decimal numbers that are represented by the BCD code below. So in this case, we are told we have this BCD code, this decimal is not there. We want to obtain the decimal equivalent, and this is very simple. We just group them into 4. And we say that the fractional part is equivalent to 7, this equivalent to 9, and this 4 equivalent to 3. So this number is equivalent to 39.7, and that is our decimal number that is represented by the BCD code. The next example is still asking us to obtain the decimal number that is represented by this BCD code. This is 1010, this is equivalent to 10, and this is equivalent to 5. And since we notice that 1010 is not a valid BCD code, then we say that this is not valid BCD code. Sometimes you might be given a tricky question like that wants to test whether you understand what forms a BCD code. Therefore, in this case, we can see 1010 is a 10 that is not a valid BCD code, and therefore it is not usable as our BCD.